Thanks to our colleagues from Taiwan Space Union to make this very cool video to welcome tonight's speaker, Dr. Ting-Yun. And today we also have a special chair for our webinar. Katza. So now I just give all the time to our host. Please to introduce our speaker. Thank you.
Yeah, today we have speaker from Durham University. She has a wonderful English name, Sunny. Yeah, so I will call her Sunny, if you permit. And Sunny received her master degree in astronomy from Tsinghua University in 2016, then PhD degree from Nottingham University, UK in 2020. Currently, she is a postdoctoral researcher in the University of Durham. Sunny is an expert in morphological classification of galaxies using machine learning. And she created one of the largest morphological galaxy catalogs using machine learning. And her today's talk is Beyond the Hubble Sequence, Machine Learning, Artificial Intelligence for Galaxy Morphology. So after the Sunny's talk, we will have about 15 minutes for questions. Please prepare your question and enjoy the talk. Sunny, I give you what now?
Yeah, thank you very much. So let me share my screen now. Yeah, thank you very much. Hello, everyone, and I'm Sunny. I'm a postdoc at Durham University, and thanks, Katya, for a very nice introduction. Thank you very much. So today I'll be talking about a series of work that using a variety of machine learning techniques on galaxy morphology. So this is the work basically based on my PhD work. And the works mentioned today is a joint effort with many great collaborators. Here I just list them at the bottom left. In particular, my PhD supervisors, Chris Consulas and Afonso Aragon Salamanca. So just a brief background knowledge. So there are over 100 billions of galaxies in the observable universe. So each of them is quite unique with distinct structure, color, and the stellar populations. So the structure of a galaxy is basically the direct result of their formation history and is strongly correlated with their stellar content. And in order to understand how these structures are formed and transformed, the first step we need to have an accurate categorization of galaxy morphology, such that each categorization can well represent a certain evolutionary path of a galaxy. Yeah. All right. So where were we? Yeah. Okay. So we really need a very accurate categorization for galaxies in order to understand what the physics behind them. So for the past centuries, visual classification such as this famous Hubble sequence is the most famous, most popular visual classification we use in galaxy studies. So from here, from the left to the right, you can see like elliptical galaxies. And then we have like lenticular galaxies, which you don't have clear spiral arms, but with the disk structure, they look a little bit like ellipticals, but a little bit different with disk inside that rather than a bulge. And then to the right, we got spiral galaxies, which as the name, you got the beautiful spiral arms there. And then we also got spiral bar galaxies, which means they have a bar structures inside the central of the galaxies. And then in the end, we got like irregular galaxies, which basically is the type. We can't define, we can't really put them into the previous types. So we have a separate type called irregular galaxies. And for historical reasons, elliptical and lenticular galaxies, we also categorize them as early type galaxies, ETG, and others at the right, we call them late type galaxies, LTG. So here, just as I mentioned, galaxy morphology is a very fundamental properties of a galaxy, which it reflects the evolutionary path of these galaxies. And the morphology of a galaxy can basically represent, like, for example, a galaxy at a different evolutionary stage, or indicate the environment of a galaxy that it is located in. So here just a quick examples using the TNG50 simulations, and this is for just like forming a single massive galaxy. So the bottom right corner shows the stellar and the gas component, and which you can see that it shows a different morphologies forming at different cosmic times. So the main panels here, oh sorry, the main panels here just shows like all the density of the cosmic gas, but roughly just tells you an idea that your gas morphology will change throughout the whole cosmic times. And so this part just also a brief thing to tell you that the galaxy morphology connects with different galaxy properties. From the left is from ego simulation, but basically talking about the same things as the TNG50, that at different, on this merger tree, at different redshift, that the same galaxy and its progenitor was forming as different galaxy morphology, depending on which stage they are in, which environment they are in, what interaction they have with their environment and with other galaxies. And from the right, that we show a galaxy zoo results that especially showing that different type of galaxies, like early type and late type galaxies, they showed a different color, which represent indicating a different stellar component. So now we know galaxy morphology are quite crucial, important in galaxy studies, and as everybody knows that we are now stepping into a big data era of astronomy. So the famous galaxy surveys such as Sloan data, in the beginning we have about 50 million galaxies. And currently largest samples of galaxies we got is from dark energy survey, which we got about 500 million galaxies. And in the future, we are looking at, for example, Rubin-L SST, that they will produce potentially 20 billions of galaxies. So this is obviously quite a big number. But how does visual classification does in astronomy? So in 2010, visual classification catalog from Nair and Abraham, they visually classify 14,000 galaxies, which you can see is a very, very small number using Sloan data. And then in order to boost the numbers, Oxford University carry out this Galaxy Zoo project that they successfully use a citizen science, which is means with that general public to help us classify galaxies, and using statistical analysis in order to boost the number, we successfully go to about 900,000 galaxies in the end. But still, again, it's still far from what we can really achieve, because in the future we are looking at over millions galaxies coming. So start from 2015, that development. So Galaxy Zoo, they released this challenge, like Galaxy Zoo morphological classification challenge. And in 2015, developments, they use a machine learning technique called convolutional neural network to try to approach this problem, and they get a good success on that. And that is also the moment convolutional neural network as a quite a nice tool be introduced into galaxy studies, and in particular the galaxy morphological classification. And after that, there are a lot of different papers just come out using the same technique with different approach and different strategies. So in this work, the first part of the talk, just a brief warning, we got about 3 parts of the talk, and hopefully I can get into it in a good, nice flow. And the first part of the talk, I use imaging data from dark energy survey. We use year 3 data, which covers, if you look at the top pictures, which roughly covers about 1/8 of the sky. And this is about 3 times bigger than the year 1 data if you look at the bottom left plot. So we also have a better spatial resolution and deeper depth than Sloan data. So as mentioned, we have about over 100 million galaxies images. And even you apply some redshift and quality selections, the initial data sets still contain over 50 million galaxies for this research. So it is like undoubtedly we have to use a machine learning approach in order to analyze this huge number of data. So we start with investigating different kinds of supervised machine learning techniques to try to build an optimal classifiers for this data. We test 6+4 machine learning techniques on the binary classification of gas in morphology. So in this task, the training data is a single band dense imaging. We use only I-band images because the reason for this is because partially due to the computational limitation, but the big reason is because we try to avoid any potential contamination from the color information. So if you work on galaxy studies, you may know that, as also I mentioned, that there's a correlation between galaxies morphology, visual morphology, and their color, but it's not unique. We still got some exception, for example, like red spirals, blue ellipticals. So that's the reason why we want the machine to only capture the structure, and we want to avoid any potential contamination from color. So we stick with only single band images, so that our machine can just pick up only the structures. And the training labels is from the Galaxy Zoo 1 project. So I won't go through every single details here because of time. In this talk, we focus only on the, actually, probably can't see my arrow. Okay, so we only focus on the leftmost techniques called convolutional neural networks, short as CNN. And if you are familiar with machine learning, it's probably not surprise to you that CNN is the most optimal machine we got, and where we get the initial accuracy of 95% for binary classification. However, I also want to note that so at the right, there is a RF indicating random forest. So just in our test, we show that simply by input galaxy pixels, random forest can reach over 90% accuracy, just a few seconds training, which is much shorter training time than the convolutional neural network. So in the case that if you don't need top accuracy, but you want a quick examination, random forest is actually can be more feasible for effective than a convolutional neural network. So choose your tool wisely. That's basically what I want to say. Okay, so just in case people in the audience that are not familiar with machine learning, and convolutional neural networks quite important concept in this talk throughout, I would like to spend a few minutes just to ensure everyone has the same basic level of understanding about what exactly it is. So CNN is a type of supervised machine learning, as I mentioned, which means that we provide labels or / prior knowledge to train the machine. So that's basically look at neural networks first. So neural networks is basically asking what are neurons and how are they connected. So here we just use a quick examples that each circles represent the neurons, and the lines in between just basically means the connection between them. So this is like a quick like pictures to show neural network structure. So neurons, you can imagine that is just something that contains a number, and the numbers that we also can annotate it into a different annotations. So these numbers, eventually, if the numbers is in the output layers, it can indicate in the probabilities. And then in between, it can indicate the different features. For example, like the numbers can be indicating, for example, the color of a galaxy, the magnitude of a galaxy, etc. And so how are they connected? The two different neurons in the two different layers, how are they connected, as we use a linear relations in between. So the first neurons of the first layer, which is the blue ones, the first neurons of the first layers is based on the neurons in the previous layers. So they do the calculation using these linear relations. The product of the weight and the neurons number and plus a bias. So eventually you will have multiple linear relations which will form a big nonlinear functions, which is your neural networks. And using this, eventually you will derive with the starting input, you will derive the output values And depending on what you want to be the output values, which in a classification situation it usually is probabilities, then you can using that to indicate how possible your new input is a certain class or not. And then what is the convolutional part? This is even easier to imagine, I think. So here I just create a quick show videos using this website that so convolutional layers trying to do is basically like your camera filter. You apply this layer to focus or emphasize some features in an image. For example, the age, or in the selfie filters, you might want to make your face, some certain part of your face being brighter, etc. So during the training process, machine will learn to find how to extract the best representative features using these convolutional layers, and that can help to classify these images. So that's basically what convolutional layers is doing. And combined together, they can efficiently extract the features from images and then connect these images in order to provide the best output, like probability. So I hope this very, very brief introduction help you understand what is convolutional neural networks. And if you forget everything I say later in the talk, hopefully eventually you remember what is CNN. So let's come back to the project. So this is the CNN architecture used for our binary classification task to classify dense imaging data. So we have convolutional layers and the dense layers for feature extractions, and the output layers will output a probability of how possible the input image is elliptical or a spiral galaxy. And as I mentioned, that initial accuracy was 0.95. So we further investigate our initial CNN classifier to see if we can further improve the accuracy. So there are a couple of perspectives we can investigate. So for example, the first one is from the chaining perspective. So the work uses images with a combination of different scales, such as gradient, logarithmic, and linear, in addition instead of only input linear images to train our machine. So from the right image, from the right plot, you can see that if you only input a linear, which is the row, or gradient, which is the HOG, they are relatively relatively worse performance than the one of combine, which is the top one. So the combined one provides a better true positive rate when you have a specific probability thresholds on this plot. So basically, the closer to the top left corner, the better performance is. So you can see the combined one actually is the closest one to the top left corner. Oh, sorry. And then other common strategies are also applied in this work. For example, balancing the number of data between different types. So which means the elliptical and the spiral galaxies is about 1. The number of them is about 1 to 1. And of course, data augmentation as well. And in this work, we also investigate there would be, so from the left plot, it shows that there would be an upper limit about how much you can improve using the same data set for data augmentations. So eventually, we just use the upper limit numbers we can do. And then finally, we set probability thresholds to exclude galaxies with low predicted probabilities. And so eventually, we increase our accuracy to about 0.987. And another perspective, so that was about training perspective, how you can further improve your training. But another perspective is about the labels we use. So this is basically asking, are the labels we use 100% correct? And in our case, it is obviously not, because Galaxy Zoo labels rely on visual classification and statistical correction. So additionally, we also found that the better resolution and the deeper depth of test data, reviewing some spiral structure that were not visible in the Sloan data. For example, in the plot we show here at the left. So the left one is the test data, and the right one is the Sloan data. They are exactly the same galaxy, but on the screen you should be able to see that the DES data shows a clear spiral structure that's just not visible in the Sloan. So if you look at, as a Galaxy Zoo volunteer, if you look at the Sloan data trying to classify these galaxies, it's likely you would say it is elliptical galaxies or elliptical galaxies or bulge-like galaxies. But if you look at the DES, then it's very likely you would just say this is a spiral galaxies. So that caused a bias there. So as more and more upcoming data with a better quality, this is something we really need to keep in mind about the label biases that's caused by image quality. But regardless that after the corrections, we found about 2.5% of galaxies in our training data needed an update using the DES data. So eventually after the corrections, our CNN classifier reached an accuracy of over 99%. So here, in order to help the later discussion, we just note that the intermediate galaxies, such as lenticular galaxies, were not really defined in the Galaxy Zoo. So these corrections basically make these intermediate galaxies into spiral galaxies class. So although we still call them spirals, but we actually is doing disk galaxies and elliptical galaxies binary classification. Just to want to make this clear. Okay, so as Katya mentioned that using this methodology that we built one of the largest catalogs for galaxy morphology, and which includes about over 20 million galaxies in our samples. Some few things to note that our CNN are trained on bright galaxies, the one that overlapped with Galaxy Zoo samples, so they are basically bright and low redshift. And because of that, and the DES data is much deeper and much fainter, because of that, we have to be very careful to examine our samples in order to make sure it's trustable in the different domains, like phantom magnitude and higher redshift, slightly higher redshift. So first of all, in the data selection, we use the most pure high confidence galaxies in the DES catalog in order to make sure to reduce possible contaminations in our data. And then we also carry out some visual classifications in different magnitude bands in order to see if machine is doing something right. And from here, that this plots the button is showing the Sussex index distributions. And if you don't, some people don't know about Sussex index, it's basically an indicator for a galaxy structure. So the smaller number around 1, 2 means it's disk galaxies, spiral galaxies. And if there's around 4 or larger than 4 is more elliptical galaxies, bulge-like galaxies. So the button, so the key thing we want to see is only the bottom one with the number miss there, the bottom one. The bottom one is a Sussex index that of the mismatch samples between visual classification and CNN output. So the rate means that visually we classify it as elliptical galaxies, but CNN say they are disk galaxies. So from here you can see when you go to a phantom magnitude, CNN actually identify disk galaxies when visual classification actually failed to do so. So this kind of proves that our machine is actually doing something right and even better than human can do. So eventually, after a lot of different examinations, that we finalize our catalogs, which include about 20 million galaxies, and then within a certain magnitude bins and the redshift bins. So just a quick summary about the first part. That so there are about 2.5% labels in the Galaxy Zoo dataset request an update. This basically shows that there is a strong bias in our labels given the different data quality. So when you are doing the machine learning, especially in galaxy studies or other studies, you need to be very careful on that. And our CNN classifier reached an accuracy of 99%, and with this, we built one of the largest classification catalog. And it is a public accessible catalog, and there's data management if you are interested in using it. And we are not the only teams who works on galaxy morphological classification catalog. So in that, we have two different teams, and we both use CNN, but with very different approaches. So we see this as a good advantage to let's compare our work to see we both have a very large morphological classification catalog for the same data set and using CNN, but different training strategy in CNN. So let's see whether we can know about some tips how to use CNN more wisely in galaxy studies. So in order to compare two works, there are some few things better to note is what is the main difference between the training approach. So let's call my work is C21. And as you already know that we use only high confidence galaxies. We only use single band images and on bright galaxies, but with different scales. So we include logarithmic, gradient, and linear. And we have using galaxy corrected galaxy 1 labels. And so you got the ellipticals and then spiral, which including disk galaxies. But for the other team that we call them V21, they use medium high confidence galaxies. And one of the big significant difference is they try to simulate bright galaxies into phantom magnitude in order to that machine pick up that like lower resolutions region. And they also use a GRI band 3 different color band images to train their machine. And their training labels is an output from another machine learning techniques. And they classify ETG and LTG, so early type and late type galaxies. So there are a subtle difference between our training strategies. So this part just basically quickly tells you that because of the data selections, we do have a big difference. So by combined both catalogs, we actually reach about 30 million galaxies. And the total intersection samples is only 60%. So that in the later discussion, we'll be focusing on these intersection samples in order to make the fair comparison. So one big question would be, do we really agree with each other? So here we show the agreement between two catalogs. And so if you look at the gray bar, it basically shows that in all different magnitude beings that over 92% we agree with each other. And the phantom magnitude, you probably can see that the blue lines indicating that the blue lines that's going up is indicating that the agreement is largely driven by a large number of spirals and late type galaxies, which also means that in the phantom magnitude being, both catalogs, both CNN tend to classify galaxies into spiral galaxy, into disk galaxies. And then we further check the confusion matrix, which is just like putting their classification and our classification into a 2x2 matrix to see how good we agree with each other. So you can see that things break down after magnitude 19. And so, of course, that would be something interesting to investigate what exactly happened. And we realized that the significant mismatch happened, in particular in the case that V21 say they are early type galaxies, but C21 say it is a spiral galaxies, it's a disk galaxies. So if we look at very naively, if we think about, okay, what is the definition of early type and a disk? So if you go back to the Hubble sequence and take a look, okay, early type and the disk, it seems like is so early type will be the red box, and the disk would be, roughly speaking, the green, blue circle. So it seems like, okay, there's an overlap about lenticular galaxies. So this mismatch actually lenticular galaxies, which is a class that is not, it doesn't exist in both catalogs. So we just further examine this possibility. So here you can see that the blue shading area at the left plot shows that the mismatch of our samples. And we use a quantity that's derived by one of their papers that using another machine learning techniques that try to understand if the probability of lenticular galaxies, if these galaxy sample are lenticular galaxy or not. And that the shading part, you can see like very large samples, like very high chances they are actually lenticular galaxies. And so at the right, we show some visual just examples for you to see that's how their structure, visual structure looks like. But when we go to the phantom magnitude, things can get a little bit tricky. For first that, because the structure measurements we have from DES is only using single fit, but in order to tackle better on these topics, you probably need to use a double fit in order to get a better representation about how structure looks like in the galaxies. So things get a bit tricky in that sense. But roughly speaking, we can say that they do follow a trend. The Suss index do follow the trend of the bright lenticular galaxies. But of course, it's still difficult to give a robust confirmation. Another thing is the elasticity things change after I band fainter than magnitude 19. So it seems like that they do have a lenticular gases property, but it's difficult to tell. But at the moment, we can say that there's a hypothesis that at least at the bright galaxies ranging, we can confirm these mismatch are actually lenticular galaxies. But the fainter than 19, we can't really be sure, but they are likely to be as well. And for the other type of mismatch, that so the type that they classify as late type galaxies, we classify as elliptical galaxies. That it does shows more like it shows more bluer colors and the lighter, less massive stellar mass. So it does shows features of more like late type galaxies or at least early spiral galaxies. So it seems like they can be this galaxy face-on or intermediate type. But at the same time, we also discovered that there might be the improvement from the V21 because they do simulate the bright galaxies into the phantom magnitude, which potentially provide them better ability to distinguish some subtle difference. So this situation is consistent to the phantom magnitude, but we noticed something quite interesting is that when you go to the phantom magnitude, even though if we believe that the V21 is doing a better job in this sense, but there is a bimodal distributions showing in the Suss index, which is indicating that there is just a misclassification happening there. And we note this is because although you do simulate galaxies into a phantom magnitude, trying to match up with the data quality, but the diversity of galaxies does not change. You still use the same set of data. You still use the same set of galaxies. It cannot well represent about what happened to the phantom magnitude or to the higher redshift ranging. So that is actually another problem we discovered in this work. So to conclude about this part, that we discovered that chaining with single band images can be as effective as multi-band images. And in my opinion, it would potentially there's bias because you try not to involve any color information. We cannot entirely confirm about phantom magnitude part, but one thing we can be sure is machine learning is proved to be able to push their prediction limits further to what we believe that, so we trained on the bright galaxies, which is like magnitude 18, but we at least can be sure we can push the prediction to at least 19. So they can push further to their training domain. And the mismatch samples are in fact lenticular galaxies. And this opened the door that if you have some classes are just very ambiguous and difficult to define, this is a different approach. You probably can just train a two separate classifier with slightly different definitions in labels and try to find the the intersections of their definitions in order to identify some type of types that is just difficult to really precisely define it, and that would be some different approach to work. And we also found out that there are a lot of different training strategies we can use and in order to approach to the phantom magnitudes, but we never be able to truly representative in our training set, because by the end of the days, we don't really know what's going on in the phantom magnitude in the higher redshift. So things can get quite tricky in terms of how you prepare your training samples when more and more new survey data is coming. For example, like JWST is totally unfolding a new regime of a galaxy morphology. So how are we going to deal with that? That would be a new issues. And in this paper, we just briefly suggest hydrodynamic simulation might be actually a good first approach. I mean, it doesn't really represent what exactly real universe is, but it can be good enough approach about some hypothesis about what the galaxy morphology can potentially be at different domains than the observation could achieve. So far, based on this comparison of two big massive catalogs, it seems like supervised machine learning is doing not too bad, and we get a good amount of numbers of galaxies that are classified and that we can use for galaxy studies. But what exactly is the problem with it? So as we just mentioned a lot, that machine learning is all about data. So if the data does not show the real diversity of the galaxy in the universe, we actually don't know when or where it could cause a problem. And that is a big problem. So how good is our training data sets become the really big issues in supervised machine learning. And secondly is about how good are the training labels. So like in our earlier talk that we mentioned about, can they really represent the true answers we are looking for, or we are training? So is it really the true properties that we are training the machine for? So how accurate these training labels is? Are they trustworthy? This is also another problem about the supervised machine learning. And in other perspectives, that it is also connected to this last issue I want to point out. For supervised machine learning, the precision of the definition of labels is very crucial in order to provide the accurate decision boundaries in the feature space. So we know that using prior knowledge is very powerful. One big thing about astronomers good is because we have this collection of prior knowledge, and we know we can interpret the data in a much higher level. This is very powerful. And so that is also why supervised machine learning is very successful in a variety of applications. However, it can also be restricted and cause some biases in our prior knowledge. For example, how good is our prior knowledge? Do we really understand what's going on inside the universe? So in our case, that one can ask how good or how precise a visual classification scheme, such as Hubble sequence, really is. So that inspired me to the final part I want to talk about is, so I start with this question, just how would a machine categorize galaxy morphology? Would that be better than visual classification can do? So first of all, so I used the approach unsupervised machine learning to approach these questions. For people who are not familiar with machine learning again, so supervised machine learning, as we just mentioned throughout for about 30 minutes, is basically you have the labels from so for example, at the left plot, you label the dot as a blue or orange, and then you try to find the decision boundaries in this feature space, which is the shading of blue and the orange, in order to separate them. And any new dots that fall into either blue or orange, we classify that as blue or orange respectively. But unsupervised machine learning is totally different case. So it will be in the same dot, but without any color. So without any indication, any labels whatsoever. So the only thing you can do is trying to find the similarity between two dots. That's basically is the distance between the two dots. Usually you're doing is the distance in the feature space between the two dots. The closer they are, we say they are more similar to each other. Then eventually with this concept, you are able to draw, for example, a radius, draw a ball, that range that we define as a cluster, that we say within this cluster, the galaxies have similar property, similar structure, etc., similar features. So that's the approach of unsupervised machine learning. And then in this work, we specifically use something called autoencoder, vector quantized birational autoencoder to be specific, to extract some useful features from the images. And then we carry out hierarchical clustering. And also for people who are not familiar with autoencoder, it's basically just like two convolutional neural network structure. And the encoder part basically trying to extract useful features from images. And then for the outputs, that you use another convolutional neural network trying to reconstruct the images using the features you just extract. Then eventually you compare the input and the output and then trying to see if they are close enough to each other. And if they do, if you can reconstruct the images very well, that means the extracted features are very representative. So that's the concept. We just use these extracted features to feed into the hierarchical clustering in order to see, to find some correlations between these features of galaxies. And then, so three main strategies are using this work, which successfully make this work provide more promising results than the previous work, which I will talk about later as well. So first one is we considering the clustering results spontaneously when learning the features from images. And I will go through really quick here because this is a quite simple concept. So that is the architecture of our autoencoder. It looks very complicated and it is quite complicated, but don't worry, don't need to know much. Basically, you just need to know we input the image, we extract some features, and we use these features to reconstruct the images. That's the key concept. But while doing this process, whenever we got the extracted features, we do a quick clustering, trying to put these features into two groups in the feature space. And we want these two groups to be well structured while learning the new features. So that's basically what the first strategy trying to do. We want to find features that not only well representative to the input images, but also can be nicely separated into two main groups in the feature space. So that's the first one. And the second one is we use a different distance threshold on this merger tree. So as we mentioned that the unsupervised machine learning is about that similarity between two dots, the distance between two dots. So which distance you use would determine about how big your circle is. And that is what happens on this merger tree we showed at the red box. So in most of the time, if you use a already built-in algorithm, that will use only one threshold. But in this work, we try to specify different threshold at different branches. Then that will go to then the reason for that is because probably you can easy to imagine that if you have, let's say, elliptical galaxies and the spiral galaxies to group, the elliptical galaxies, within the elliptical galaxies, it doesn't really show much variation. Because if you have an elliptical, you rotate it, it still look at elliptical. But if a spiral galaxies, that would cause a lot of different variation, which means that the spiral galaxies can be, the spiral arms can be 2 spiral arms, 3 spiral arms at this orientation, at this orientation, at this orientation, then everything will cause different variation in the image, in the 2D projected images you look at. And that will result in the different distance in the feature space you should use. So in other words, is that if you use only one single distance threshold, you will produce redundant clusters in the you would produce redundant clusters for the elliptical case, but you will probably not enough cluster in order to separate the spiral galaxies, different type of spiral galaxies well in their case. So different distance is quite important to use. Yeah, but the next question would be, where I should put the threshold on this merger tree. Where is it? It will be quite crucial in this sense. So in this work, that in order to make it fully without human involvement, fully unsupervised, so we calculate something. We calculate values using the variation caused by the gas rotation. The idea is that quite simple. That so sometimes you look at the galaxies. There are some type of galaxies that they look just simply rotate a little bit. For example, like the examples here. And this type of galaxies, they're supposed to be the same type if you look at the structure. So we don't want a machine to separate them into two different groups just simply because they rotate a little bit. And we just calculate the variation caused between this rotation and find this number, and in order to draw, using that number to draw a line on this merger tree. And in this idea that you will be able to create, you have to separate the machine class that without any impact of gas rotation. So hopefully that makes sense to you all. But that is how exactly we decide which distance threshold we should use. We use that gas rotation information. And eventually we get 27 machine classes fully unsupervised without any human involvement. And it's obtained using monochromatic Sloan images, so using only R-band images. And we examine that is definitely focus on only gaseous structures and gaseous shape. They are separated based on gaseous structure and gaseous shape. So this is quite a good improvement and provide more promising results compared to the previous work. What is that? So the previous work from this one is other people's work. They have about 160 machine classes. And because it's so many that they have to carry out a further visual classification on these 160 classes in order to make sense of it. But this machine, this unsupervised approach, that they provide 27, which is totally a feasible and reasonable number for galaxy morphology. So that's why we say that it provides the three strategies we use provide a more promising result. And then we look at the physical properties of these 27 machine classes, and it shows distinctive physical properties. For example, with the monochromatic images, this unsupervised machine just separate galaxies with different colors. So you don't train machine with colors, but based on gaseous structures, machine be able to separate galaxies that with different colors, which means different stellar populations. And that's something very, very interesting we found out in this work. And also to examine the correlation of this unsupervised machine categorization with the visual classification scheme like Hubble sequence, we defined a quantity called dominance to assess what dominant visual features are in the machine class. So to read this plot, each bar represent each different color bar represent a machine class. So the x-axis shows what kind of visual features a machine class possess. For example, that's the leftmost, there are two different color, two bars. So it means two machine classes have the visual features associated with elliptical and lenticular galaxies, both lenticular and elliptical morphologies. And the we also separate different bar dominance. So that shows in the different type of blues. The deeper blue shows that the galaxies in the machine class has a stronger bar features by visual classification. And so from this, you can see that the bar galaxies can be well separated into different classes by machine. So here again, just a quick examples about machine class with different bar dominance. So if from the top to the bottom is no significant bar dominance, and to the strong bar dominance in the machine class. And secondly, we also note that galaxies with similar structures, which means they are in the same machine class, can be visually classified into multiple visual morphologies. So this actually shows there's intrinsic uncertainty of visual classification. In particular, like if we look at these 4 classes here, so 4 bars. So the leftmost 2 classes show visual features of elliptical and lenticular galaxies. And the middle one shows dominantly a visual feature of lenticular. And the rightmost shows the combination of lenticular and early spiral galaxies. So we further investigate the Suss index distribution of these machine classes. It shows that when doing visual classification, only very moderate, very right structure, the yellow line here, it can potentially avoid confusion with other visual type. So in other words, that only this very specific galaxy structure can be classified, visually classified as lenticular. Any other galaxies actually share similar structures as other visual morphologies. This shows that a strong ambiguity in how a visual classification schemes used to define their galaxy morphology. So this just basically tells you that a visual classification scheme is not quite accurate and precise in choosing their decision boundaries, which probably you can imagine because it's defined by human visually looking, right? So again, this just shows that the intrinsic problems is not only visual classification, but also the scheme, the standard we use for visual classification. So the summary of this part of the work is that firstly, we have 27 classes, machine classes, obtained from the monochromatic Sloan data. And the decision boundary is totally drawn numerically and on a high dimensional feature space that human is impossible to achieve. And we can separate different bar strengths. Each class have a distinctive physical properties. And most important is that this research shows that there is an intrinsic bias, intrinsic ambiguity in our visual classification scheme. In order to push our galaxy studies further, we really need something more accurate, more precise to categorize our galaxy morphology. So the follow-up work, which is ongoing work at the moment, is I'm working on building this APRA machine learning classification scheme to provide something more objective and precise and reliable within different survey, different data quality, etc. things to categorize our galaxies. And promise this is the final summary that of everything, the 3 parts I told. So CNN is a very useful tool as long as you know what you're doing, including what kind of training data set you use, how you prepare them. And so there are a couple works I worked on that can provide some tips of how to you train your CNN and how do you approach in making a good performance in your galaxy studies. And we have a big catalog that is publicly accessible if you want to use it for your science. And eventually that the final part is just some discussion point about where unsupervised machine learning can provide a different approach to galaxy studies. And from here, we shows that it's yes. And this research provides new interpretation to galaxy morphology. And furthermore, it can potentially help us understanding better what mechanisms is causing this morphology by simply just categorizing them in a better way. So more update will be coming soon. I will skip this part because it just basically say I also work on other things as well. But if you're interested in it, feel free to contact me. And that'll be end of my talk. And thank you very much. I'm happy to take any questions.
Thank you, Sunny, for the nice talk. We have a few questions in the chat. If you have any questions, please don't hesitate to ask, because Sunny is a very good expert in the field. You can leave your question in the chat or just raise your hand. So, and I will read the first question. Is it okay to use like CNN classifier or open CV in government science research plan, which have business composition in it? Kind of tricky question.
Yeah. In terms of function, yes, I believe you could, depending on whatever images you're looking at and what talk you're looking at. But I'm not sure. Is this question is more about government's data is sensitive? Do you mind explain more about your questions?
Open CV in government science research plan. Is it okay to use like?
Yeah, I mean, it's definitely okay to use CNN classifier. I mean, it will work, for sure. And then, but it depends on what kind of data set you are using. CNN is specifically used for 2D, two-dimensional images type of things, and also CNN is quite limited to in terms of functionality. CNN is actually only focused on local features. So if you look at the images, what conversion layer is doing is actually they pick a box and then convolve all the pixels around that box. So as you can imagine, CNN is only focusing on localized features. But today, if your data is something that needs a wide range of correlations, for example, like language, like a translation algorithm type of things, the keywords will not be right next to each other. It sometimes can be quite far away from each other. And in that case, CNN would not be a good choice of technique to use. So if that's what you're asking, so I would say it's basically, if you are going to use it, for sure, it should be okay. But you really need to understand what features you cared about and how their spatial distribution is. And then also, with these really the tools you need to use, because sometimes a simple tool like a random forest would be even more efficient and cost effective to help your case. Yeah.
Okay, let's move on. Cindy is asking, can I use CNN classifier to train high redshift galaxies?
Yes, again, definitely you could. But high redshift galaxies have there's a different type of limitation in terms of like data quality. If you're not using JWST, then most of time in the survey data, redshift higher than, let's say, 0.4-ish, you'd only see a blob, and unless you use very good resolution data, like if you use ground-based, probably HSC, you can get more details. So the thing is, the question would be, yes, of course, you could use CNN classifier, but again, is your training data really have a quality to showing some detailed structures that is meaningful and the machine can pick it up? A lot of time in my research, because we push to about redshift 1, it does show that even though individually you see a blob, but machine can pick up some these structures outside this blob than human eyes can do. So up to 1, I can tell you that's okay. CNN classifier can do, at least for dense data, for dark energy survey data. But if higher than that, then you need to find a good data set in order to that machine to learn corresponding features to tell what kind of structure they are. Yeah.
Okay, right now we have no other questions. Oh yeah, we have. So user Cheng is thanking you for the talk, great talk, and he says, I wonder what is the most challenging part for you to do the machine learning in your projects?
So I think that the most challenging part probably is the last project I was talking about, the unsupervised approach. It is actually quite difficult in a way that in supervised machine learning, you have labels, you have prior knowledge. Machine know what they are looking for. But in unsupervised machine learning, machine has a problem to find some features that machine feel it makes sense. But for human, we try to interpret it, which doesn't find it make sense. So the very challenging part is there are a couple of things. So one is it's difficult for unsupervised machine learning to find some features that astronomer cares about. Yeah. So machine can find all the different relevant features can contribute to the result. But again, do astronomer cared about that? Astronomer cared about the things that can correlate with physics. So if there's something that machine identify, but it's not really correlate with physics, or at least we doesn't think it does, then it's tricky for us. So that's one difficult part. And the second part is so at the moment, unsupervised machine learning has a difficult breakthrough because again, we don't know what exactly is the number of galaxy morphology we should have. So that's a really tricky question. In a very extreme situation, you can say every single galaxy is one class, but that doesn't make sense and that wouldn't help the galaxy studies. So the thing is, what is the number of types galaxy we should have that it can provide the correct or accurate physics behind these types, and but at the same time it can also be concise enough to really put it's tricky to have the right number, and then that numbers may also be changed at different redshift as well, so in different cosmic times. So that's actually challenging things to do and challenging to answer, and that's also the reason why that in other people's work they have 160 classifications, and in our works that we're really trying to put that down the number, but how do you decide the final number is tricky. And in this work, we leave this decision to the machine, to the numerical calculation. So that's why we use a galaxy rotation in order to draw a threshold in order to decide the number of galaxy types. So that I would say that's two parts that I found it really, really difficult in unsupervised approach. One is like to find the meaningful features that's meaningful in terms of astronomer found it meaningful. And second is the parts that how many type of galaxies is what we're really looking for in galaxy studies. Yeah.
Thank you for the answer. Okay. Thank you, BTV. I like what you described the unsupervised machine learning about similarity. So he's thanking you.
Thank you very much.
Yeah, any more questions? Please don't hesitate to ask your final question. I find the question from Cindy was quite interesting because when we look for high redshift galaxies, we usually look for dropouts in one of the photometric band. So CNN technique which use 3 or more bands, they probably can't classify them because they assume, because they assume that that object should be detected in all bands, right?
Exactly. So that is one thing that I was having hesitate in that type of approach. For example, like a lot of they do normalize individual band individually, so try to avoid the color information as well. But when you input the data at different band, and so especially this data got a different redshift range. So at different bands, you do have a different structures show up depending on redshift, which redshift you are in, and depending on what type of galaxies you are. So that is something that I believe you will leak color informations. And so that's why I stick with single band. And at the same time, single band will be having a really good approach, for example, like the space telescope type of things. And when you, for example, go to a higher redshift, you technically you only want to be limited in a certain band in order to focus on certain redshift as well. Yeah, so that's why single band approach is quite crucial for galaxy structure, I would say.
Yes. Thank you for the answer. So, any more questions? No, I don't see any new questions in the chat. So, we probably can close the meeting because the time is over.
No problem.
Thank you to the audience, for those who attended the meeting and asked the questions. And thank you to our speaker for the very nice talk and very detailed answers.
Yeah, no problem. Thank you very much.
Thank you very much.
Thank you. Bye.
Thank you.
Bye.